Okay, welcome to note set 6, where we'll start using all the methods that we've learned so far, all the ideas that we've learned, to take a look at how we solve AX equal B. Don't let this note set make you think that this is simple, because we're going to spend a good portion of the course doing nothing but looking at the ideas behind solving this. So we'll look at a lot of different tools, and hopefully you'll see that it's more than just how do I get the answer. It's where does the answer come from? Why do I get the answer the way that I get it? When can I get an answer? When can't I get an answer? And how do I understand what leads to the conditions that when I can get an answer. So the stuff we'll be talking about in this set of notes is covered in section 1.3 of the textbook. So we've already talked about a lot of the key ideas that are important for exploring how to solve AX equal to B. We'll continue learning more key ideas as we go into this. But the ones that we've done so far, well, we've defined, scalars, vectors, and matrices, so we know what those are. We've talked about the idea that a set of vectors could be linearly independent or linearly dependent, and we at least have the idea of how to check that, although we don't have nice mechanistic ways to do it, but we've got a pretty strong concept of that. We have this idea of linear combinations of vectors, and the idea of linear combinations is tied together with the idea of independence. So the way that we check, that we know so far to check for the independence of vectors involves looking at linear combinations of them. And if you remember, the key thing was if the vectors are linearly independent, then the only way to form a linear combination of the vectors that equals 0 is to set all of the coefficients equal to 0. So that's a key idea, and that'll pop up here. And then our view of matrix times vector, AX, when we multiply A times X, the elements in X are the weights in a linear combination of the columns of A. So in other words, when we say AX equal B, what we're doing is we're saying we need to pick the X values such that they are the weights that will form a linear combination of the columns of A just right, so that that linear combination will solve or will give us B. If we don't pick the right X values for those weightings, we'll get some other linear combination of the columns and it won't add up to B. And so, believe it or not, that's actually the key to understanding how this all works. Now, there were some other things in the previous note sets, not to say that they're not important, but they're not things that we're going to be focusing on right here. So, we talked about inner product, and we talked about length and angles and so forth. So those will be important elsewhere, but in this set of notes, it's these 4 things that we're focusing on. What we're going to do is kind of sneak up on this solution of AX equal to B and get some initial insight into how it works by just exploring 2 simple examples. Examples are nice because they kind of let us see the machinery in work. But the examples that we look at in this set of notes will later be explored more deeply in more general ideas in some of the later notes. So we're not, in this set of notes, we're going to just start getting a flavor of this. We won't be able to explain everything here, but it'll set the stage for what we do later. So here's our first example for the AX equal to B. So we're going to pick three vectors, u, v, and w. So I apologize for this being non-italic and this being italic, but that's just how it worked out, and it would just be a pain to go through and change all the italics to non-italics. I did think about it though, but it'd be an awful lot of time. So they were created this way, and that's how I'm going to run with it. Now, also notice that when I'm just reminding you again that when we write things like this with parentheses and commas, it's just a shorthand, compact way of writing what is really a column vector. So, so when we write this, what we really mean is a vector that has 1, -1, and 0 as a column vector. Okay, it's just easier to write it out on a single line that way. So we've got these three vectors, and what are we going to do with those? Well, we're going to imagine forming a matrix A that has those as its columns. And since we've got vectors with three elements and we've got three of them, this matrix A will be a square matrix. And that's the case that we're looking at here for right now anyway, when we say AX equal to B, it is by assumption that A is square. So given A defined this way, we can write out the AX part this way. And you'll notice that we're just using symbols for the X. That's because we don't know what it is. And so if we do our by hand multiplication, we're going to take these three elements and lay them out across here, so that the first element of the result will just be x1 times 1, 0 times x2, and 0 times x3 gives us just x1. And then the next one is going to give us a negative x1 plus an x2, so that's what we have here. And then the next element will give us 0 times x1, negative 1 times x2 plus x3, and that gives us that there. So let me clear this out here. So if we do this multiplication, we get this form that looks like this. And then that's the thing on the left side, set equal to B. So this, for this particular matrix, is just another way to write the scenario that we have. And from that, we can actually get an idea of how to solve it. But we can also see that we can view this with the linear combination view. So we have our by hand view that got us to this view, and we also have the x1 times u, so there's u that gets multiplied by x1, and then x2 times v, and x3 times w. And so this linear combination gives us b. And so in this form, we're asking, given u, v, and w, and b, find the x1, x2, x3 values that cause the linear combination on the left to be equal to the given vector on the right. And so we've got these two ways to view this, and the first view, this by hand multiplication, for this particular A leads to a very simple solution. And then the second view, this linear combination view, that's what will tell us as we go through this why this works, and we'll also explore a case when this doesn't work. So it will start to give us some insight into the behavior of how this works. So same A, we're just continuing on here. So suppose we're given this A and some specific B, and we're asked to solve for X. Find the X that solves this. And I'm just pointing out here that, this is a lot harder than being given A and given X and just doing the multiplication to find a B. So even though we need to think about the machinery for A times X, what we really need to do is somehow get X isolated by itself. And so if we rewrite this as a set of equations, we can use tricks we've learned in past math studies, maybe in your high school math, or at some point in a previous college class, you learn how to solve a set of linear equations like this. And this one is particularly easy to solve, and that's because of the structure of this matrix. We see that in this lower triangular part is where we have the non-zero values, and the entire triangle above the diagonal is all zero. So we call such a matrix structure lower triangular matrix. So this lower triangular form of A makes the resulting equations very easy to solve. And in particular, it's this first row that has just 1, 0, 0 that leads to this very first equation, which is very easy to solve. In fact, it's solved already. The instant you write it down, it's solved. x1 is equal to b1. And then, because of the lower triangular nature, the next equation has only 2 terms in it. And so that's the x1 and x2 terms. So we have this is equal to b2, but remember we already know this, so we have only one unknown variable in that second equation, and so we can solve that and find out that x2 is equal to b1 plus b2. Now we know x1 and we know x2, we've solved those already, and the third equation, it actually only has 2 terms in it, but we could still solve this even if this 0 were something else, because we already know x1. So, we could have an x1 term out here, but in this case there is a 0 there, so we don't have it. But nonetheless, very easy to solve for x3. And in this case, we see that it equals b1 plus b2 plus b3. Okay, so you give me a b vector, and I just plug in its 3 elements, and I've got my solution. So again, as I'm saying, the point of what we're doing is not to just find the solution. If that's all we're interested in doing, we're done. And to be honest, you can just run some software. MATLAB will solve this for you, but you will lose the insight that everything else we're going to talk about will give you. And look, engineers are not about just getting a numerical answer to the problem. They're all about understanding why it works the way that it works, and coming up with insight into how to make things work better. So understanding why things work the way they work is part of being an engineer. So why does this work this way? Well, we've already explained to some extent that it's easy to solve because of the lower triangular nature of the matrix, which leads to a set of equations that's very easy to solve, one step at a time. But why is there even a solution? How do we know when we set out to solve this that there are some x values that will do this? So that's kind of what we want to look at in this and explore a little bit more. So if we look at this, we can see that this will work for any given b vector. As soon as you tell me what the b vector is, I just plug its values in to these slots, and I instantly get the x1, x2, and x3. And in particular, if I said, well, all right, let's say b is equal to the 0 vector, well, then it's easy to find that the solution is 0, 0, 0. If, on the other hand, I pick b is equal to 1, 3, 5, then it's easy to apply this set of equations to find what the x1, x2, and x3 values are, and write them down. And we can do this for any given b vector. Like I said, we're sneaking up on these ideas. Later we will define this idea of invertible matrix. And so what we'll find is that any time the A matrix, so this is our A matrix for this particular problem, anytime the A matrix is what's called invertible, we'll be able to solve this problem for any given B on the other side. And so whenever matrix A is invertible, we can recover X from any B. And so, if we can find this magic inverse of A, so we'll call that the inverse matrix. Once we have that, to solve for X, all we really need to do is take this inverse matrix and multiply it by B, and bing, it gives us the X. So if we go back to just a regular equation, X is equal to B, and here A is just a given number. X is a single variable, not a vector. B is a single given number. How would we solve this? Well, we would say there is a magic inverse that gives it to us. So we would say that X is equal to A inverse times B. And this A inverse, well, that's really just 1 over A. And in the number case, we can write it as that reciprocal, or that fraction, 1 over A. In the matrix case, we can't really do that because that idea is not well defined. Dividing a vector by a matrix is not defined. But there will be this concept of there will be a new matrix that will be called the inverse matrix of A that will work when I pre-multiply B by the inverse matrix. It'll give me back the X. And so that's where we're going here. So let's dive in a little bit farther into this to see what the inverse matrix would look like for this simple example. So here's our solution. Here's the equations that we had. And here's our solution to that we deduced for this simple problem. And if we look carefully at this, this is just combinations of the elements of B. So if we think about it, we're looking for some matrix over here that will multiply B to give us this structure for this problem. And so it's pretty clear we can deduce, I need to select out one B1 and none of the others. So my first row will be 1, 0, 0. Because remember, to do this multiplication, I'm going to imagine rotating this thing around and putting, B1 here, B2 here, and B3 here, and then forming the pairs. So B1 times 1, B2 times 0, B3 times 0, and add all those up. Well, that gives me this. And you can verify that it works for the other ones as well. So this row here gives us B1 plus B2, and then this row gives us B1 plus B2 plus B3. So we can verify that our guess as to what the inverse of A is correct. So you give me the vector B, and I just smack it with this A inverse matrix, multiply from the left. We haven't really talked about multiplying from the right, and that's not always possible, as we know, but sometimes it can be. But in this case, we're multiplying from the left, and later we'll see why we need to apply the inverse matrix from the left. But this will give it to us. And so now you give me any vector B, and I just have to smack it from the left with A inverse, and I get my solution. And the author of the textbook likes to point out at this point that, if you look at the A matrix, it's like taking differences between adjacent values of x, or adjacent elements of x. And if you look at the inverse matrix, it's like taking sums of the elements of B. And so he goes into a little aside how this difference matrix and sum matrix are kind of reverses of each other, kind of in the same way that differentiation and integration are reverses of each other. So that's a little aside that's not terribly important, but you can pay attention to it if you want or not. Let's look at our second example. So far we didn't really need to focus on the linear combination view at all, but that's mainly because this first example was very simple and it was nice and easy. Let's change our matrix. So we're going to keep the first two columns the same, and we're going to change our third column. So the first element was a 0, and we're now making it a -1. So now if we form this matrix, this new matrix, which we'll call C. I mean, we could call it A, but so now we're going to be doing Cx is equal to B. So here's our Cx. We now have our new elements in here, and now if we do the by hand multiplication, we can see that that's the condition, and we end up with three equations. We could write down three equations for these, and we see that in this case our C matrix is not triangular, and therefore it's not simple to solve by hand. So it's not obvious whether what the solution is for this, and this is not just because it's not triangular, but we have a bad situation here. This particular matrix C doesn't lead to a nice simple solution like the matrix A did. A, there was you give me a B and there's just one solution for the x vector that solves that equation. Here, you give me a B, I don't know whether there's a solution or not. There might be, there might not be a solution. And if there is a solution, it turns out that there isn't just one unique solution for that given B. There's infinitely many solutions. So when I say infinitely many solutions, I don't mean because we're changing B. I mean for you give me one fixed B vector, and there are infinitely many x vectors that will satisfy the Cx equal to B equation. Now that's just weird. And so we need to take a look at that. But it's not much different than the scenario, say 0 times x equals 0. Well, there's an equation that has infinitely many solutions. In fact, any x value, including x equal to 0, will solve that equation. It's not a particularly interesting equation, but that's kind of the scalar analog to what we're talking about here. We've got a scenario, we've got a matrix C that isn't the 0 matrix, but it's kind of behaving like it has some aspects of being 0-ish. It's a made-up word, 0-ish, but I think it conveys the basic idea. And remember I said when we go into this new domain of vectors and matrices, we need to make sure that things how things work are consistent with what we saw before, but some things might get more generalized. So in a scalar equation scenario, this is pretty clear and fairly limited. We have to have a 0 here and we have to have a 0 here in order to get many solutions. But when we go to Cx is equal to B for some special matrix C that's kind of got a 0-ish characteristic to it, and we'll see what that what we really mean by zero-ish characteristic to it. We don't necessarily have to have a purely zero matrix and a purely zero vector over here to get to the case where we have infinitely many solutions. So let's explore this a little bit farther and see if we can make sense of why this is happening and how it works. So let's look at this. Here's our equation, and let's look at two scenarios. So let's pick b equal to 0. When b is equal to 0, we find out that there are infinitely many solutions. In fact, any vector x that has all three elements of it the same will solve Cx equal to 0. And that's because, if x1 and x3 are the same, that becomes 0. And if x1 and x2 are the same, that becomes 0. And if x3 and x2 are the same, that becomes 0. So we can easily see this, and it doesn't matter what the value of c is. So for any constant c, you stick it into all three positions in the x vector, and you get something that solves this. So there's infinitely many solutions. Now, notice that we picked a b here whose elements all summed to 0, obviously because they're all 0. But it turns out that if we pick some b for which the elements don't sum to 0, then there will be no solutions. So, look at what we have. If we look at this up here, and all we've done is brought that down here for a specific b vector. If we look at the left side, well, if we add those elements up, we're going to get x1 minus x3 plus x2 minus x1. So notice that those cancel. Plus x3, so those cancel. Minus x2, those cancel. And what are we left with? 0. So the sum of the elements on the left is equal to 0. And so that must mean for there to be a solution, the sum of the elements on the right side must also be equal to 0. But I picked a b for which they don't. So there is no x vector for which this will work. No matter what x vector I pick, there's no way I can make it satisfy this equation. So that's a case where there are no solutions. So suddenly we see two different scenarios. I picked one b and I got infinitely many solutions. I picked another b and I got no solutions. Well, let's back up to our previous slide. Remember when we were talking about 0x is equal to 0? Well, what if I said 0x is equal to, and instead of 0, I said 5. Now, there is no x for which that equation is satisfied. No matter what I pick for x, I will get 0 times that x, and there's no way that can be equal to 5. No solution. So again, we're seeing that we've got a scenario here where, like I was saying, the given matrix here is behaving zero-ish. Again, I'm making this term up, the zero-ish term, but we'll resolve what we really call that in just a bit. But it behaves like this. And this is one of the cool things about doing this kind of math, is that the mathematicians took the scalar equations and expanded them into a new, direction, almost literally, making matrices, along two dimensions, two directions, and we've retained some of the characteristics, the fact that some equations have solutions, some have infinitely many solutions, and some have no solutions. But we don't need to have a true 0 here on the left side to make that happen. We just have to have some sort of pathological C on the left side. And here is one of those. So for something that looks like this, That's that pathological zero-ish matrix that causes these problems. What is it about that matrix that makes this a problem? That's what we want to look at. Well, let's compare the two cases and see if we can puzzle it out. It's not just that one is lower triangular and the other one isn't. That's not it. I'll tell you that right from the beginning. It's something deeper than that. So for this first example, we showed that we could find an inverse matrix so that, here it is. And we can apply that inverse matrix to any B, and it's just a matter of doing multiplication to give us the solution. That's beautiful. It's simple. On the other side, we found out that if we picked all zeros for our B values, then we could find infinitely many solutions. So there wasn't just an inverse matrix involved. And remember, this kind of links back to, remember, our 0 times x is equal to 5. So if you take future courses from me, you'll discover that chances are pretty high. If I have to pick an integer, I'm going to pick the number 5. I don't know why. I like the number 5 for some reason. But can we solve this? Well, remember when we had, if we had like 2x is equal to 5. How do we solve that? Well, we divide both sides by 2. So 1 over 2, 1/2 is kind of the inverse of that coefficient out in front, 2. The 2's over here cancel, and we're left x is equal to 5/2. But up here, what can we do? We cannot divide by 0. There is no inverse of 0. There's an inverse of 2, but there's no inverse of 0. There's an inverse of this matrix, but there is no inverse of this matrix. Why is there no inverse of that? Well, we'll see that in just a bit. So when we cannot find an inverse matrix, so if we have a matrix and there is no inverse, we call that matrix singular. So there's the true term that I'm looking for. Not that it's zero-ish. That's a made-up term that I literally just made up as I was recording this video lecture. Hadn't planned on using that. That's just kind of how these video lectures go. I wing it sometimes. But singular. So the matrix is singular means we cannot find its inverse. And by the way, when we can find the inverse matrix, we say that it's non-singular. So it's kind of interesting that the defining term is applied to the case where things don't work, singular. And then the case where things work, we use the non in front of the defined term. So that always struck me as odd. I always felt like they should have called it, used a term for the case where it works, and then used the non such and such for the case where it doesn't work. I guess it's, I don't know. I guess the case where it didn't work was the more interesting one, and so people were focused on that, and when they discovered that idea, they said, oh, we need a name for that. And what we found was that not only could we not find an inverse matrix, but sometimes there was a solution and sometimes there wasn't a solution. So when we had 0x is equal to 5, no solution. But 0x is equal to 0, infinitely many solutions. Same kind of thing here. So for this given C matrix, depending on our choice of B, because remember up here, it depended on whether I put a non-zero element here or a zero element here, determined when I did and didn't get solutions. Same thing down here. Depending upon what I pick for my B determines whether I will have infinitely many solutions, which I saw in this case, or no solution at all. So why this difference? Well, Remember I told you that the linear combination view, so sometimes I abbreviate combination by combo. So the linear combo view shows us why. That's the power of that viewpoint that allows us to really understand the machinery that's going on. And not just for these two examples, but for everything. That's the amazing part of this. So let's take a look at this. So what do we see here? Let's use the linear combination view. So here are the columns for the first case, and we limited ourselves to three-dimensional vectors so we could visualize this. But this holds regardless of how many dimensions you have and whether you can visualize it or not. So 4 dimensions, 5, 6, 1,000, 1,000,000, it doesn't matter. The ideas hold, but obviously if we want to see those ideas in action, we need to limit ourselves to no more than 3 dimensions. So here they are. Here's our U, here's our V, and here's our W. Now a little bit of explanation. It's hard to view these three-dimensional renderings. So we've got 3 axes. We've got the 1 axis here. We've got the 2 axis and the 3 axis. So those are just regular right angle axes that we normally have for our three-dimensional case. Come on. What's going on there? Why can't I get that? Not letting me. Well, I wanted to erase this, but it's not letting me. All right, there we go. I got it. Oh, goodness, that was difficult. So there's our three-dimensional axes. And so let's look at this. We've got our U, which is a 1 along the 1 axis and a -1 along the 2 axis. So this vector here is actually lying in the plane formed by those two. Okay? So keep that in mind. All right, let's see. There we go. That's working a little bit better. So that's U. Here's V. It lies completely in the plane formed by the second and third. So here's our second axis. Here's our third axis. And so if we think about those as being on a wall, a vertical wall right in front of us that we're standing in front of, this vector would be on that wall. It wouldn't stick out of the wall, it wouldn't stick into the wall, so it lies in the plane set by axes 2 and 3. So it's a +1 along here, and then down -1 along that axis. So it's a little hard to see. All right, let me clear this up here. There we go. And then finally, our W vector is only along the third axis. So it points straight up. So again, if 2 and 3 form, think of that as being on the wall that you're standing in front of. The W vector would lie on the wall and point straight up. So clearly, there is no plane that holds all of those vectors. Now, when I say holds all of them, what I mean is holds all of them that they lie completely in. It's not that they touched. I'm not talking about a plane that touches just at the tips. I'm talking about a plane that they would all lie in. So W and V both lie in a plane that is the wall that's right in front of me. But U sticks out of that wall. So there's no plane that would have all 3 vectors lie in it. Now let's look at the second case. So I've got the same U and I've got the same V. The only thing that I changed was W. I changed it to something called W star. And the only thing that's different is this. And so this no longer lies perfectly along this axis. And in fact, it no longer lies in this 2-3 plane. because it does have a contribution along the one axis. So it does stick out this way some amount. So, if we were standing in front of the wall, this thing would not point left or right, but it would be kind of like falling out of the wall towards us, I guess is the right way to say that. But anyway, it's not obvious, it's not easy to visualize this, but my claim is that all three of those vectors lie in a plane, and not only that, that plane actually goes through the origin. So when we're talking about these vectors lying in a plane, the planes that we're talking about have to go through the origin. And so, this graphic from the textbook is trying to convey that idea, but it's a little hard to see it. But if we had all these vectors and we were talking about this wall in front of us, this plane would actually kind of jut out of the wall going upwards and jut into the wall going downwards. So hopefully you can visualize that. But our linear combination view will allow us to see that this is the case. So remember, here we have three vectors that do not lie in one plane. There's no plane that holds all three of those vectors. Therefore, we know that the columns for case 1 are linearly independent vectors. That was our definition, our initial definition of what linear independent meant for three vectors. Three vectors are linearly independent if there is no plane in which they all lie. And that's the case for the first case here. But remember, we said here that all three vectors lie in the same plane. So clearly, case number 2, the vectors that form the columns of our matrix are linearly dependent. They're not independent. And that's the key to this. So that zero-ish characteristic, that singular characteristic that we finally came up with the right technical math term, singular matrix, it's because the columns of the matrix are not linearly independent. Or to say it in a more, without using a not, the columns are linearly dependent. And let's just see this. So over here I'm saying since UVW are linearly independent, let me back up here. There is no way to there is a way to combine them to form any vector B. So there are three vectors in three-dimensional space, so that are linearly independent. You give me any B, and there are values, unique values of x1, x2, and x3 that will allow me to build B from these three vectors. This is the key idea, the key view. It's the linear combination view. But what about over here? Well, as I said, U, V, and W star are not independent. And oh crap, I should have put a star here. I'll have to fix that in the notes that I post. So there should be a star there. There should be a star there. U, V, and W star are not independent. And remember, so our first inkling of that was, they all lie in the same plane, three vectors in the same plane. But then remember we said a better way to think about that was there's no way to build any of their, for each of the vectors, there's no way to build it from the remaining vectors. But look, I can take negative V minus W star, and that'll give me 0. So negative V, that gives me a negative and a plus, minus W star. So let me just negate it, and then we'll think about adding it. So I'm going to negate that, and I'm going to negate that. So now let's add this modified vector to this modified vector. So I get a +1 in the first element, matches. I get a 0 plus a -1, gives me a -1 in the second element. That matches. I get a -1 plus a +1 goes to 0. So sure enough, that is true. So that is another indication that the columns of the C matrix are linearly dependent. And then remember the last way, and perhaps the best way to characterize linearly dependent or linearly independent, was to look at a linear combination of the columns, or the vectors in this case, and we said that for them to be linearly independent, the only way we could weight them and add them, the only linear combination that would give 0 is if 0 was the coefficient for every one of them. So to make this 0 over here, if they were linearly independent, we would need to put a 0 in front of each one. But we don't have that. We simply have, let me clear this off here. Let me do an eraser here. All right, good. We simply have, come on, there we go. We have 1 times u plus 1 times v plus 1 times w star. It's not important that they're 1s, it's important that they're not 0s. So, and one of them could be 0, 2 of them could be 0, but all 3 of them can't be 0 if they are linearly dependent. So, in this case, they're not all 0, and I can still make 0, therefore they are not independent. Okay, so that means they all lie in the same plane. So the only thing I can build from them is something in the same plane. Now 0's in that plane, so I can build 0. I mean, you see that, right? I can build 0. That's why there was a solution. In fact, I can put any C here. We talked about that on the previous slide. I can put any C here, and they'll still add to 0. So if I weight them all equally, no matter how I weight them, they'll add to 0. So we saw that x is equal to c was a solution, but only when b was equal to 0. So 0, 0, 0 is this origin. It is in the plane. But if I pick a b outside the plane, remember, there's no way, I don't have any contribution from these 3 vectors that allows me to poke outside of that plane. So there's no way I can build that from these 3 vectors. Therefore, there is no solution for that case. And this is the crux of it. And we got there just by looking at this linear combination view. So it boils down to whether the matrix is linearly independent columns or linearly dependent columns. When we have linearly dependent columns, we say the matrix is singular. There is no inverse matrix that exists, and we cannot solve it except for a few special cases. But we can't solve it in general. So if B lies in the plane, then there is a way to combine the columns to form it. So if we picked B is equal to 1 minus 1, 0, that lies in the plane. You can check that it does. And one way to check is that there is a solution. I can build that from picking x is equal to 1, 0, 0, 0, because I can take, basically b is equal to this column. So this vector will select this column and multiply each of those by 0. So there's our linear combination view helping us visualize that works this way. But x is equal to 2, 1, 1 also solves. And in fact, remember we said that CCC, if x is equal to CCC, it gives us equal to 0, 0, 0 after being multiplied by the C matrix. So any x vector that maps to 0, 0, 0 can be added to this solution, and we'll also solve this. And you can double check that. And we'll explore these ideas deeper as we go in. So we're just kind of creeping up on this. But this says that there are infinitely many solutions for any vector that lies outside of, any vector B that lies outside of the plane in which u, v, and w star lie. So for any B that lies in the plane, then there are infinitely many solutions. So basically that's just saying that there are infinitely many ways that I can combine three dependent vectors to form a vector that lies in their plane. But if it lies outside of the plane, there is no way to combine those three vectors to form that outside of the plane vector B. And so there is no solution. So all of this insight comes from the concept of independence together with the fact that A times X forms a linear combination of the columns of A. And remember, we used linear combinations in the definition of our concept of independence. And so that's what links these. So we can summarize this like this. If A has independent columns, then there's one solution. In other words, a unique single solution for each B and for any B. You give me a B, there's one and only one X that will solve that equation. And we say that A is invertible or non-singular. So those two terms mean the same thing. If A has dependent columns, then there will be infinitely many solutions for any B that lies in the plane of the columns. And in particular, since B equal to 0 must lie in that plane, AX equals 0 has infinitely many solutions. Now, you move that B outside of the plane, and there is no solution for that. And in this case, when we have dependent columns, A is not invertible. There is no matrix that we define as the inverse of matrix A. And we'll nail down this concept of inverse matrix a little more precisely in a later set of notes. And we call this case singular. We say the matrix A is singular. For the independent column case, we say that the matrix A is non-singular. So this is the view that will drive almost everything else we look at in this course. So I would encourage you to spend some time thinking about it. Thinking, not memorizing. If you just try to get this in your brain through rote memorization, you're setting yourself up for much more difficult time later. Think about it. You're smart. You can think this through. You need to be able to think about it. And here's one nice way to visualize this. This is our last slide, and I like to draw pictures. When I'm working out math, I'm always trying to draw little diagrams that help me navigate through the concepts. And so for these things, I like to make these little, kind of bicursion diagrams. I start from one place and I split. They're not always splitting into two. Some things I have to split into more cases, but we start off with AX is equal to B. A is square. X and B are appropriately sized vectors. So our first decision should always be look at the matrix A. Does A have independent columns or dependent columns? If it has independent columns, we say A is non-singular. A is invertible. And I don't care what B is, there is a solution. And a unique solution. By me saying one solution, I mean one solution per B vector. Change the B vector, get a different solution. But there's not two different X vectors that will solve it for one specific B. So that's what I mean by one solution. On the other side, A columns are dependent. So A is singular. A is not invertible. And now we've got a decision after that. So then we get to this point and we have to ask, what about B? Ah, crap, I said Y here. This should be B. I'll try to fix that in the notes before I post them. I borrowed these from some other notes that I had for another class. B, not in the plane of the columns of A. If that's the case, then there's no solution. B is in the plane of the columns of A. Then there are many solutions. And how many solutions? Infinitely many solutions. So for each, I'm talking about for each B, you give me one specific B that lies in the plane, there are infinitely many X vectors that will allow me to solve that one case with that one specific B. So this is where this set of notes ends, and stare at this, think about this, don't memorize it, learn it, internalize it. This is critical to the things that we're going to be talking about later in the course. All right, I'll see you in the next video.